Yeah, thank you for having me. Thank you. This is joint with Jeremy Lane, who I think more of you know than I do, and we started collaborating this in this area about 3 years ago, before beginning of COVID. Okay, so thank you to Yael and Tara for having me. Sorry, there are going to be no real geometric results here, and thank you to Rare and Jean Lerman for having birthdays. All right. So matrices we know about, but Hermitian matrices have real eigenvalues. And if you take a submatrix, upper or left submatrix, it's again Hermitian. And so it again has real eigenvalues. And these eigenvalues are interrelated in this way. They are interwoven, interlaced thus. So moreover, if you have any sets of reals satisfying those, they come from some Hermitian matrix and its Hermitian truncation. And if you iterate this truncation, you get more inequalities with the eigenvalues of the second truncation. And you can keep doing this and you get a triangle of inequalities. Now, if you fix the top row and consider all of the other numbers that satisfies the inequalities, because each inequality cuts out a half plane out of some Euclidean space, you get some polytope, right? Or by the way, yes, each of these is realized as well by some list of truncations, all the truncations of Hermitian matrix. So this polytope is called the Gelfand Zeitlin polytope. And then you think, because of this definition, here's an example. If the top three are distinct, you get this nice three-dimensional shape, which is one of the few that you can sort of completely visualize. All right, so if you write O lambda for the set of Hermitian matrices with some eigenvalue list, so this is the top, the lambda n in the previous one, then taking all the eigenvalue lists of all the truncations determines a map down to this polytope. So you can ask what the fiber of this polytope is. Right, so where does this arise? This is the geometric content, which I've just paraphrased from Jeremy, essentially. I typically don't read this aloud because it doesn't benefit anything, but motivation, yeah, comes from integral systems. There is an unanswered question that Megumi and Mark Hamilton want to deal with and momentarily had some hope for, and that seems to be receding now, but that is related to the facts. And yeah, I am ill-equipped to speak on this, but there's your geometry. Give it a moment. Okay. All right, yes, and so that's the U story. There's a version with special orthogonal matrices and skew-symmetric matrices as well. All right, so the topology of this fiber doesn't change, actually, if you wiggle the point a little. It's really what's equal and unequal in this pattern of eigenvalues of truncations that matters. So if you have the two fibers corresponding to these are the same, it's really just this shape here that determines the topology of the fiber. It's sort of intuitive that it should be continuous, but some crossing into a higher dimensional face of the polytope corresponds to some sort of change, right? And so here's what was known up until, I don't know, 2021. 2020. All right, so these are two author sets. So this thing that I just said, that it only depends on the pattern, really, the diffeomorphism type of the fiber, and that there's an iterated fiber bundle, which is this is the total space of as well. And actually, each fiber is product of odd-dimensional spheres. So what does that mean? That means that I have this tower of fiber bundles. Each of these things is a fiber bundle. Each of these vertical maps is a projection fiber bundle. And these groups H and L are block unitary groups of the corresponding bigger unitary group, such that each of these homogeneous quotients, I have a hand, is diffeomorphic to a product of odd-dimensional spheres. All right, I'm not going to say too much about what H and L are in this talk, but they're understandable. And there are also inclusions between LK and HK plus 1 that you can take to be block unitary, and that is something I am just sweeping under the rug. But these blocks are indexed by the distinct eigenvalues, which are the distinct components of the rows of this shape, this graph that I have shown you, which we call a pattern. Okay, so continuing, this gives a dimension formula. You just add the dimensions of the H's and subtract the dimensions of the L's, is known. In the unitary case, this other author set show that it's this fiber is a Cartesian product of factors indexed by components of this pattern. They have a similar graphical tool, and they have explicit descriptions in some cases, like unitary groups and a few others. So in the case of a unitary Gelfand Zeitlin fiber, again, there's a torus direct factor that comes from something called the Tim trick. And so these authors, Cho-Kim and Oh, found this direct factor. I mean, they didn't know they showed this factor as a result of a toric degeneration, which is a sort of, from my perspective, a hardcore algebra geometric result. And they used this to project onto a factor onto this torus factor to show that it exists in all cases. And this accounts for the pi1, which was the only known homotopy group. All right, so new results is we found an explicit formula for all fibers in terms of balance products, which I'll explain, of unitary and orthogonal groups, but they can be seen as double coset spaces. They're not terribly hard, and they're readable off the diagram entirely. In the orthogonal case as well, so you knew for the unitary group case, unitary system case, again, they're direct products indexed by components of the pattern. Again, you can read this off the pattern entirely, and the setup makes it sort of much more transparent than it has any right to be. There's a torus direct factor in the orthogonal case. In both cases, you can detect this from the picture without knowing about the toric degeneration. And sort of going in the other direction, just knowing about these tori gives you a way of constructing something that we only know on the topological level, but could be a shadow of the toric degeneration as far as we know. There could be up to some torus action. It seems likely that it is the underlying topological map. And this exists in the orthogonal case too, where there isn't a known toric degeneration. So this is a topological fact that's new, and I don't know if there's an overlying geometric fact. So this proof follows from a sort of weak local model for the coadjoint orbit, which is what Megumi and Mark were interested in, that again follows from the formulae for the fibers. A bit more, we have up through pi3 in all cases now, and cohomology rings. Unitary case, exterior odd dimensional generators. And if you invert to, same in the orthogonal case, but with even dimensional generators, and I can describe it as a graded group, it has only two torsion, but I don't know the integral cohomology ring in its entirety. Right, so dimension counting example with these H's and L's, these turn out to depend only on the widths of shapes here. So you have 20 of these dots, not in the top row. Oh, too far. Then you have 3 of these triangles of width 1, then 1 of these width 2 lower trapezoids, and 1 of these width 3. And this numerology tells you the dimension. And moreover, so here's another diagrammatic tool. This is Cho-Kim Oh's analysis involves a big pullback square where the thing you want is over here. And the groups we've talked about contribute to this edge. And the fibers of each of these are these products of spheres that we talked about. Right, and so they analyze the vertical maps, and that really gives them their whole analysis. And we decided to analyze these horizontal maps too. So moving this forward, so we did this in the first place to understand the cohomology, and the idea is that each of these fibrations has a serospectral sequence. Each of these squares gives a map of serospectral sequences, and you'd want to see what you can say to compute cohomology with this. And we understand the serospectral sequences over there. So the idea is you can use one to understand the other. And it turns out that all the ones along the left collapse. And that's what gives the result, which is just that the cohomology is as though it were a product of the spheres, even though it's not. But as far as cohomology can see, integral cohomology can see it is. All right. Yeah, so in particular, it's an exterior algebra. And so back to this example, just counting the dots and the trapezoids / upward facing triangles, you see it's an exterior algebra on generators of those dimensions. Right. Okay, so here's balance products. It's just a quotient under a certain action. So take a diagonal action of on a space where you have a right and a left action. We denote the elements this way. This is why, as with a tensor, because you can pass the G back and forth under this quotient. So example, if I include SO3 in upper left corners of SO4 and SO5, just filling in the ones with diagonals, then this thing is the orbit space under the action, under this diagonal action. That's what I mean. And then if you want to move it onto one side, you can. If you do this sort of familiar trick of switching a left action for a right action, and you take this diagonal SO3, you can write this as one coset space. More generally, if you have an iterated balance product, which is what we end up doing, it's going to be diffeomorphic to a double coset space. So that's the sort of most complicated manifold that shows up in this analysis. All right, so here's a motivating lemma. It's really sort of a basic algebraic fact. It says that the balance product is related to a fiber product in this way. And the idea is just that if I have something over here, I have a coset and a group element that are going to match when I project them down to this other quotient space. And that means the difference between the two of those is going to be some element in this group H. And that's, yeah, so you node G up to its coset and extract the difference. And that gives this map. This is a bijection. Then if these are topological groups, it's a homeomorphism. If they're Lie groups, it's a diffeomorphism. Okay. So you can generalize this mildly and then apply this to the staircase. And I'll do this quickly. And you keep on doing this. And you get that this is what the fiber has to be. It's this balance product, which we've seen as a double coset space of some kind. And really good thing about this is that these inclusions of LK and HK and LK and HK plus 1 preserve the block diagonal decomposition, which we said was indexed by the individual eigenvalues in the rows. So what it means is that, and so algebraic fact, given a pair of diagrams, just looking at unpacking the definition, you have this. If you have no interactions between the factors, then the balance product of direct products breaks apart into a direct product of balance products. This is just an exercise with the definitions, and it works with more of them. What this means, because these block decompositions are preserved, this iterated balance product breaks into a direct product over all of the components of other balance products. And you get a little bit more than that. So distinct components, because they involve a U0 in the thing that's being quotiented out, correspond to distinct disjoint factors. Okay, direct factors. All right, so example, fiber corresponding to this diagram has two U1 factors, U1 mod U1 factors over here, and one diamond corresponding to this. But there's a lot of collapsing. You have two U1s here, two U2s here, and two U2s here. And you get that this is U3 mod U1. So that's an S3. Wait, no, it's a CP. Anyway, all right, so there's a lot of telescoping. Here's another example with more pieces. The 5 dots and this dash correspond U1s each. And then the remaining components correspond to nothing. This, and you can always read off the widths what these are going to be. Here's U2, tensor U1, U2. Here's U4 down to 2, up to 3 down to 2. And this one is a U2 mod U1. So you always have descriptions of this form that you can just read off the diagram. All right, so torus action now. Yeah, so there's the direct factors are of these two forms depending whether or not the top is met. If you have something of this form, the U1 over here can be multiplied by some complex number, and so that gives you a torus action. And if you have T many components of these, you get an action of the T torus, and that turns out to be the known Tim-Trick action. You get that just by explicitly converting coordinates. I've brushed some details under the rug, but this is very doable. This is a free action that allows us to separate out the torus factor. And one way to do it is to notice that there's a determinant map where the ambiguities of the balance product are multiplied out, and that gives you a map to S1. Right? Yeah, so Chokim and I do this in a complicated way, and we do this in a simpler way that sort of maybe allows us to reconstruct the time one gradient Hamilton flow map of the toric degeneration just by combining all of these projections. So the difficulty is in proving this is continuous, and to do that, you need a local model of some kind. This has to do with the ways the components combine, the way the determinant map deals with that, and understanding this local model for a codimension, for the junction of a face and a codimension 1 face. Why that happens is there's this relationship between the groups, yes, that has to do with it has to do with continuity of representatives, induces a commutative diagram, induces this map, and yeah, that's it. No, that was it. And it's the mapping cylinder of this map.